Peeps, what in the heck are we going to do in this video? Today, we are going to describe what's called the self-ionization of water and describe a solution in terms of concentrations of hydronium ion and hydroxide ion. Yikes! 4 big things specifically that we need to be able to do by the time we finish this video. 1. Describe the self-ionization of water. 2. Describe the equilibrium of constant, known as Kw. 3. Describe a solution in terms of the hydronium ion concentration and hydroxide ion concentration. And finally, 4. Calculate hydronium ion concentration, hydroxide ion concentration using Kw. First, to understand whether a solution is an acid or a base, we'll use pure water as a neutral starting point. Although pure water is mostly molecules of water, obviously, conductivity measurements indicate a small amount of ions are present from what's called the self-ionization of a small amount of those water molecules. That self-ionization is described in the chemical equation that you see here. 2 water molecules interact with one another, creating a hydronium ion and a hydroxide ion. Illustrated by this animated GIF, or GIF, that you see here below. Important to note that just a small number of water molecules actually undergo this self-ionization at any given time. So when you drink water, you are in fact drinking mostly water. Very little has actually turned into those hydronium ion or hydroxide ion products. Again, important to recognize the self-ionization of water is 2 water molecules producing a hydronium ion and hydroxide ion. Important to note, the self-ionization of water produces equal amounts of hydronium and hydroxide ions, and those are at concentrations of 1 × 10⁻⁷ molar each. Because these ions are an equal concentration, we say that pure water is neutral. Equal amounts of hydronium and hydroxide in a solution means the solution is neutral. Now, at this point in your chemistry career, we're going to simplify a few things. You're going to take my word at face value that the relationship between the concentration of hydronium ion and hydroxide ions is given by what's called the equilibrium constant, Kw, and has a value of 1 × 10⁻⁴. Value of Kw is calculated by multiplying the hydronium ion concentration by the hydroxide ion concentration in solution. It's important to note that Kw is a constant, and therefore, as long as temperature remains the same, the value of Kw will not change and will always be 1 × 10⁻⁴. This formula that represents the equilibrium constant expression for the self-ionization of water, or Kw, is given to you on your formula chart, as is the value 1 × 10⁻⁴. Again, to simplify a few things, it's important to remember that Kw is a constant, and increasing either the hydronium or hydroxide ion concentration will cause a decrease in the other in order to keep that value of Kw the same. You can then determine whether or not a solution is acidic, basic, or neutral, depending on which ion is in greater concentration. Important relationships that you need to understand is that if you think about your neutral starting point as those concentrations being equal, we will classify a solution as acidic if there's more hydronium ion than hydroxide, or basic if there's more hydroxide than hydronium. So let's take a look at a little example. The example we're going to think about is an acidic solution. When you put an acid in water, it's going to ionize and increase the concentration of hydrogen ion or hydronium ion. Thinking about the equation that represents the equilibrium constant for the self-ionization of water, Kw equals hydronium ion times hydroxide ion, putting an acid in pure water is going to cause that concentration of hydronium ion to increase. In response, the hydroxide ion concentration will decrease in order to keep that equilibrium constant value, 1 × 10⁻⁴, the same. Putting some sample numbers in there, increase, decrease, keeping Kw constant. Let's take a look at a basic example. Adding a base to solution is going to increase the concentration of hydroxide ion. Keeping in mind the formula for the equilibrium constant expression for the self-ionization of water, which is on your formula chart, increasing hydroxide ion concentration will decrease hydronium ion concentration, keeping Kw constant. Let's look at example with some numbers. Bumping up the hydroxide ion concentration to 1 × 10⁻⁴ is going to cause a decrease in hydronium ion to 1 times 10 to the minus 13. So when you multiply those two concentrations together, you still get 1 times 10 to the minus 14. Boom! Here's a quick visual representation of all of those notes that you just completed. We're going to start with pure water. And if you'll notice, both on the left over here in quantitative measurements and visually, qualitatively here in solution, in pure water, there are equal concentrations of hydronium ion and hydroxide ion. They're each 1 times 10 to the minus 7 molar, equal red and blue dots over here. That's our neutral starting point. If you make a solution acidic by adding an acid, which will increase the concentration of hydronium ion, it's automatically going to decrease the concentration of hydroxide ion in response. Quantitatively, if you multiply these two concentrations together for an acidic solution, it will still equal 1 times 10 to the minus 14. Visually, you'll notice there's more hydronium than hydroxide in solution. Going back to our neutral starting point of pure water, if you increase the concentration of hydroxide by, say, adding a base to water, the hydronium ion concentration will decrease in response. Importantly, the product of those two ion concentrations will always equal 1 times 10 to the minus 14. The difference in a basic solution is now there's going to be more hydroxide than hydronium. Again, it doesn't matter how much you increase the hydroxide ion concentration by, the hydronium ion is going to respond so that the product of those concentrations will always equal 1 times 10 to the minus 14. All right, y'all, you have made it to the end. Congratulations. See you in class for some practice and lots of fun.